So this thing don't increase from 300.
Ọpẹ́ o, ọpẹ́ o, ọpẹ́ o.
Okay.
Good morning, student.
Good morning, sir.
Good morning, sir.
Good morning, sir.
No, you're echoing.
Good morning,
no,
sir.
you're
Good morning,
echoing.
sir. Good morning, sir.
Good morning, sir.
Good morning, sir.
Good morning, sir.
Good morning, sir.
So the YouTube link has been pasted to the LMS sheet. You can put it on the Telegram group so that others can join.
Okay, sir.
Let me make one or two people a co-host. Oh, so Kamiola Ade Dosu. Let me make a co-host. I think, yeah. Would
Okay.
have been regular.
Okay, sir.
So I've made you a host so you can meet anyone disturbing the class. And I think the Zoom want to take more than 300 this month.
Yes, sir.
Yes, sir.
Please.
Oh, that's great. Okay. Let's take the YouTube. No. So I think we can start. No. Okay. Good morning, students.
All right, sir.
Yeah.
Good morning, sir.
Okay.
Good morning, sir.
So come please make me a host.
Okay, sir.
Just change you to so yours put your cursor on my name. You will see 3 dots. Click on it and make me a post. Oh,
You are
thank
due
you.
now, sir.
Oh, thank you. Okay, let's start. Good morning once again. So yesterday morning I put the lecture notes and a video on the LMS page. I believe you guys have downloaded it and have gone through it. So that's what we are doing this morning. So, but before we do that this morning, I want us to quickly look at the last part of what we did there last time. So, yeah, because there was a network issue last week, and later my phone went off, so I could not listen to some of the questions you were asking. So this morning I will just run through it and move to what we have. So, okay, this is the question we solved. And somebody was saying when he divided, when he converted this value to Pascal, he did not get this. The value to convert atmospheric pressure to Pascal is 1.01 times 10 to the power 5. So that's why I say approximately 10 to the power 5. But if you use 1.05, you will get this value exactly. But at times, it just give you 10 to the power 5. So it's just an approach. I don't know if the person that has a question is in the class this morning, but that's how I got this. So 1 ATM is equal to 1.01 times 10 raised to power 5 Pascal, or Newton per meter square. So if you do that, you will see that you will get all these values you have here. So that's just the clarification, because as last week I saw many people were discussing it, but I could not answer them because my phone later went off. So that is that. So let's start today's business. Let's start today's business. So can we all see my screen? Olas, can you see my screen with lecture 3? I think Olas, we can talk now because you are a host.
Yes, sir.
Okay.
Yes, I
you can see lecture.
Sir.
Okay, lecture 3, right?
No, I think it's the previous class that we had.
That's your okay. Let me share. Okay.
Okay,
So
yes,
let's
this is
start. Okay, today's business. So this morning we are looking at the thermal expansion of solid and of liquid. So we all know that if the temperature of a liquid increases, its volume will also increase. Its volume will also increase. But there's an exception to this, which is water. You know, from temperature of like -4 to 0 degrees Celsius. When you are, from -4 to 0 degrees Celsius, water will expand just like any other liquid. Okay. Okay, let me record. Okay, thermal expansion of solid and liquid. If the temperature of a liquid increases, its volume will also increase. But there's an exception to this, which is water. When you increase the temperature of water from -4 degrees Celsius to 0 degrees, water will expand normally, just like any other liquid will do. But after 0 degrees Celsius, from 0 to 4 degrees Celsius, water begins to contract. So this is contrary to any other materials, because we believe that when you increase the temperature of a body, the body should expand. But from 0 degrees Celsius to 4 degrees Celsius, water will contract. So then after 4 degrees Celsius, water begins to expand normally, just like any other materials. And this is what is called the anomalous behavior of water that you have done in secondary school. So that's what they want you to explain when they ask you what is the anomalous expansion behavior of water. So, but for solid, as temperature increases, its dimensions also increase. This phenomenon is known as thermal expansion, when the dimensions increase, or when the volume in terms of liquid increases when you increase temperature. This is called a thermal expansion, and it has many applications. For instance, thermal joints are included in buildings, railroad tracks, concrete highways, and bridges to compensate for dimensional changes that occur as a result of temperature change. Yeah. So when they are laying a bridge, when they are laying a railroad tracks, so they always leave spaces between the tracks, so that during the hot day, when the rod they use increases in length, so they will not touch each other, and the thing might collapse. So because of that, they leave some spaces in between them to allow for expansion during the hot spacing or hot day. So let's explain. Let's look at how we can explain this. So expansion is a consequence of the change in the average separation between the constituent atom in an object. So we know that all objects are made up of atoms, and there's a separation between this atom and the next atom to it. But at absolute zero temperature, the atoms will oscillate. They will oscillate between that distance, that position, which is about 10 to the power minus 10 meter. That's like 1 angstrom. So the atoms will be oscillating about that position. But as you are increasing the temperature, the oscillation increase, the amplitude of the oscillation will increase. As you continue to increase the temperature, the amplitude of oscillation get increased until there's a considerable distance between the two atoms, and consequently we say the object has expanded. We say the object has expanded. If thermal expansion is sufficiently small relative to the initial dimension of the object, then this relation will hold. That is, if the expansion is not too much. If the expansion is not too much, if you do not supply too much energy that can cause bond breaking. So this relationship, that is change in length over the original length, is proportional to that increase in the temperature. So, and that's when if the expansion is not too great. So where delta T, as I said, is increase in temperature, delta L is change in length, Li is the original length of that material. Hence, I can write delta L over Li equals alpha delta T. From this relation from here, you can write delta L over Li equals alpha delta. You did variation in mathematics. This is just variation. I remove the proportional symbol. I put equal to, and I put a constant. The constant now is what is called a coefficient of linear expansion. Then if you cross multiply this equation, you have delta L equals alpha Li delta T. Delta T, where alpha is the coefficient of linear expansion, as I've said. This implies that this is change in length. That is, the final length minus the initial length is equal to alpha Li, then change the temperature, the final temperature minus the initial temperature. This equation and this equation are exactly the same. So, since all the linear dimensions, that is length, breadth, and height of an object change with temperature, it implies that the surface area and volume also will change. What we are saying is that if you consider solid and you increase the temperature of that solid, you know that the length of that solid will increase, the breadth of that solid will increase, the height of that solid also will increase. Definitely, the area will also increase, and the volume, the area and the volume will also increase. Similarly, as we've done in length, we say that delta V over Vi is proportional to delta T, so that I can write delta V over Vi. Delta V is the change in volume, and Vi is the original volume, equals gamma delta T. So this is just a application of variation that we did in mathematics, that I say change in volume over original volume is equal to gamma delta T. Gamma is the constant now. If I remove a proportional symbol, I put equal to and a constant. Our constant now is gamma, which is called the coefficient of volume expansion. Coefficient of volume expansion. So sorry. So if I cross multiply, I will have what I have here, delta V equals gamma VI delta. This is exactly the same as what we have here. So, but this is when we are dealing with the length. That is when we are considering only the length increases, or when we are considering object with only the length. So we say delta L is equal to alpha delta L. Likewise, when the volume has increased, so we say delta V is equal to gamma VI delta V. Where delta V, that is change in volume, is equal to final volume minus initial volume equals gamma VI change in temperature. That's the final temperature minus initial temperature, where gamma is the coefficient of volume expansion. Similarly, we can do the same to area of a solid, so that we can have delta A is equal to beta A. It should be AI, that's initial area, delta T. So in this case, beta is the coefficient of area expansion, which is still called the superficial expansion. So recall that for a solid, coefficient of volume expansion is equal to 3 times linear expansion. And beta is equal to, the beta is the coefficient of area expansion of that material, equals 2 times the coefficient of linear expansion of that material. And this assumes that the alpha is the same in all direction, meaning that, let's say you have a box. For this to hold, for this simple relation to hold, it means that the length and the breadth and the height are made up of the same materials. That is, they have the same linear coefficient of linear expansion. To show this relation, these two simple relations, we use this box below. I said to show that gamma is equal to 3 alpha, we consider the box below, whose volume is VI. The initial volume is VI at temperature Ti. So if the temperature changes to Ti plus delta T, that's, let's say this is final temperature, let's say this is our final, its volume also will change from Vi to Vi plus delta V. So this will be Vi plus delta V is the final volume as a sort of the change in all of its dimension. So therefore, I can have initial volume is equal to Vi. You know how to calculate volume. If this is a box, I want to calculate the volume of this box. So it will just be length times the width and times the depth or the height. So that's Li for initial, Wi, Di. That's why I have initial volume is this. Then the final volume, don't forget that this one, the final volume will be Li plus delta L. So this is multiplied by Wi plus delta W. This is the final width. Then multiplied by Di plus delta D. So this will be our final volume. That is, both the length, the width, and the Di have increased by little amounts, delta L, delta W, delta D. If the coefficient of linear expansion is the same in the 3 directions, as I've said, if the box, the length, the breadth, and the height are made up of the same material, that means they have the same coefficient of linear expansion in all directions. If they don't have the same, if they are not made of the same material, then that relation will not hold. You have to manipulate it to suit what we want. Then we know that delta L, in the previous slide, that delta L is equal to alpha Li delta T. Likewise, delta W will be alpha Wi delta T, and delta D also will be this. We now substitute all this in this equation star. Wherever you see delta L, put this in there. Wherever you see delta W, put this one there. Wherever you see delta D, put this one there. So if you do that, we have what we have here. So, but if you look at it, I have Li here, I have Wi here, I have, okay, Li here, Li here, Wi is here also, Di is here, Di is also here. I can factorize Li, Wi, Di out of the bracket. So if I do that, I will have what I have here. So we have this. So if you look at this, we have the same thing in 3 ways. So I can have Li, Wi, Di bracket 1 plus alpha delta t raised to power 3. Raised to power 3. So if I expand the term inside the bracket, I will have 1 plus 3 alpha delta t plus 3 alpha delta t square plus alpha delta t raised to power 3. So I believe you know how to expand this. This is just a very simple expansion. And if you don't know it, you can just use a Pascal triangle or binomial theorem to expand this simple expression. So you have this. But you remember that delta V is equal to the final volume minus initial volume. I believe you remember that. What will now be, what is our final volume? All this is our final volume according to what we have here. So minus the initial volume, this initial volume. Then you have Li, Wi, Di here. You have it here too. You can factorize it out again. So I just factorize all this out, and I have, if you factorize this one will be 1. This minus 1 will now cancel this one. So you have what you have inside the square bracket. Inside the bracket. But you will see that Li, Wi, Di is the initial volume. So if you divide both sides by initial volume, you have delta V over Vi equals 3 alpha delta t plus 3 blah blah blah, and to the last term, which I call the equation star. Equation star. So what you did is just divide both sides by the initial volume. And this is initial volume. If you divide by initial, it will cancel. Then the initial volume will be here. That's why you have this thing. This thing is just the term you have inside the square bracket here. So which I call the equation star. But we know that alpha is usually very small. Yeah, it's very small, like 0.00001, 0.0, very, very small value. So if it's very small, that means this value and this value will be it will be extremely small. It will be so small that we can neglect them. So if we apply that, so we say the second term at the right hand at this term that I just said, and this term, and this term will be very small compared to alpha delta t. Therefore, they can be neglected. So that equation star becomes what we have here. So that means I can have delta V over Vi is equal to a constant. This is a constant, delta t. If you go back to where we have delta something over the original, is equal to a constant delta t. So for instance, we have it here. You can see it. We have it in the length. So the change in the length over the original length is equal to a constant delta t. So exactly. So in this case, 3 alpha is our constant, which is represented as a gamma. So that's why we can have delta V over Vi is equal to gamma delta t. That's how they derive this gamma of 18 that they always give. You know, many in most cases they will not give you a gamma. They will not give you coefficient of volume expansion. What will they give you is linear expansion. They want you to know this relationship and apply it. So I put one assignment here that I've shown how gamma is equal to 3 alpha. Then in a similar manner, it can be shown that for a rectangular plate, the change in the area can be written as this, where beta is 2 alpha. So please, you have to show that as I've done. My own is more complex than your own is just the area. Just do it and submit it to the LMS page. So let's look at this simple problem. If a segment of a steel railroad track has a length of 30.00 meter when the temperature is 0.0 degrees Celsius. So if you have a question, please reserve your question to the end of the class, please. So they said a steel railroad track has this length as the original length, that's Li, where the temperature is 0.0 degrees Celsius. What is its length when the temperature is 40 degrees? So I believe we know what to do. Then suppose the ends of the ray are rigidly clamped at 0.0 degrees Celsius so that expansion is prevented. What is thermal stress set up in the ray if its temperature is raised to 40 degrees Celsius? The Young modulus of the steel is given to be this, and the coefficient of linear expansion is given to be this. Yeah, this is very, this might not be familiar, but what they are saying is that let's say they clamp the railroad track at the both end, so that when the temperature increases, the thing will not expand. The thing might want to expand, but because you clamp it at the both end, the thing will not expand. So there will be a kind of stress that thing will be passing through. So they want us to calculate that stress. Then the last one was the length of the unclamped segment if the temperature drops to minus 40 degrees. That is, instead of temperature to increase to 40, what would be the length if the temperature drops to minus 40 degrees? So let's look at that. Okay, the first question. So what is the length when the temperature is increased to 40 degrees? So they want us to find the final length. So you remember this relation that we just finished now, delta L over Li is equal to alpha delta T. So that when I cross multiply, I have delta L is equal to Li alpha delta T. Just put the value, they give you the original length of that track, which is 30.0 meter, times the linear, the coefficient of linear expansion, which is 11 times 10 to the power minus 6, as given in the equation, and this is temperature change. The initial temperature is 0, and temperature increases to 40. So change in temperature is 40 degree. So when you put it, you have your delta T, delta L to be 0.013 meter. So the final length will now be 30 plus the increase in the length, which is 30.013 meter. So that is that. Then the second question is saying we should find the thermal stress if the both end of that track is clamped. The both ends are clamped so that the expansion is not allowed. So, and I said the stress is the same as tensile stress in the situation in which the ray expands freely. That is, how can you get this? The way you tackle this, that you look at it as, oh, what if I allow expansion? What will be the tensile stress? So tensile stress that you will get if you allow expansion is the same thing as thermal stress that thing will be passing through if you do not allow expansion. What we do is just calculate the tensile stress from this simple relation. Oh, sorry, I wrote Young modulus 2 times. Young modulus is equal to tensile stress over tensile strain. So that's why they give you Young modulus in the question, but you know how to find tensile strain. Tensile strain is just a change in length over original length. This thing can be called a tensile strain. Change in length over the original length. So when I cross the line, I see tensile stress, which can also be calculated with this formula, force over area is equal to the Young modulus times the tensile strain. So just multiply, that's Young modulus times tensile strain. So the Young modulus is given to be 20 times 10 to the power 10. While the tensile strain can be calculated using the 0.013, that's change in length over 30 original length. So if you put all this value, you have just multiply this by this and divide by 30, you have what you have here. Then the question C is saying, what if the temperature drops by minus 40 degrees? or drops by 40 degrees. That's the temperature reduces to minus 40 degrees. So the process is still the same as the first process. So the change in temperature, let's go back to the question. The change in temperature is still 40. The track was at 0.0 degrees Celsius, and the temperature drops to minus 40 degrees Celsius. So the change in temperature is still 40. So you get the same change in length. That is, your delta L will be the same as what you have here. But instead of adding it to the original length, you will now subtract it as I've done here. So this is very simple. It's only that the temperature drops. So the original length will be shorter than the the final length will be shorter than the original length. Sorry, somebody is disturbing with the call. So that's why I have 29.987. So let's look at this question again. A poorly designed electronic device has two bolts attached to different parts of the device that almost touch each other in stereo, as shown in the figure. The steel and brass bolts are at different electric potential, and if they touch, a short circuit will develop, damaging the device. The initial gap between the ends of the bolts is 5.0 micrometer at 27 degrees Celsius. At what temperature will the bolts touch? Then take the coefficient of linear expansion for steel and brass respectively to be 11 times 10 to the power minus 6 per degree Celsius and 19 times 10 to the power minus 6 per degree Celsius. Yeah, what they are saying is that this is a device that is poorly designed. So this is the steel bolt, and this is the brass bolt. So there's a very little gap between them, which is a 5.0 micrometer, a very little gap between them. It's 5.0 meter. So at a particular temperature, if the temperature increases, you know that this length, this bolt will increase, the length of this bolt will increase, the length of this one will increase. You get a point that they will touch. And if they touch, because they are at a different potential, it can damage the device, and damage the device because a short circuit will develop. So they now say we should find the temperature at which these two bolts will touch each other. What I will do is that I will calculate a change in the length of this steel bolt at that particular change in temperature. I will calculate this one at that the same change in temperature. If I add them together, it must be equal to this 5. When this one increases a little, this one also will increase a little. So once the increase in length of this plus this one is equal to 5.0 micrometer, they will touch. They will touch each other. Okay, let's look at the solution. At a particular change in temperature, that's I call the change in temperature delta T, the steel will increase in length by delta L. Remember the formula delta L is equal to Li alpha delta T. But I put S to indicate steel. So that's why I have delta LS is equal to LIS alpha S delta T. For brass also, I have delta L is equal to Li alpha delta B for this bolt. So, but I put B to indicate brass. So if I had this delta L for the steel and delta L for the brass, if I get 5.0 micrometer, so the two bolts will touch. So let's go on as it. So I say delta L for steel plus delta B, delta L for brass is equal to 5.0 times 10 to the power minus 6. Micro means 10 to the power minus 6. That's why I put 10 to the power minus 6 there. Then this is the formula for delta LS. This is formula for delta LB. At the same change in temperature, don't forget. So I have this. Then I factorize delta T out, that is the common temperature. I factorize it out. and it's equal to 5.0 times 10 to the power minus 6. So divide both sides by what you have inside the bracket. You have what you have here. The length of the steel is given. The coefficient of linear expansion for the steel is given in the equation. Likewise for the brass, the two are given also. Just put the length of the steel is 0.01. So if there is written there, so the length of this steel is 0.01 meter, while that of brass is 0.030 meter. So that's why you have. So this is for the steel 0.01. The length times the coefficient of linear expansion for the steel plus the length of the brass, that's delta, that's Li for brass times 90 times 10 to the power minus is the coefficient of linear expansion for brass. So when you do this well, you will get 7.4 as the change in temperature. So, and the question is, at what temperature will the two bolts touch? So you go and look at the initial temperature and add this 7.4. The initial temperature given in the equation is 70 degrees Celsius. So let's look at it. The initial gap between the end of the bolt is 5.0 micrometer at 27 degrees Celsius. So this is the initial temperature. When the temperature increased by 7.4, the touch, that's I need to add the 7.4 to 27 before I get the temperature at which the two bolts will touch. Yeah. So this is another exercise for you to do. Oh, sorry, there's an exercise here. Okay, question 2. You see that I did not solve this question. Please go and lay your hand on it. So the active element of a certain laser is a glass rod, 30.0 centimeter long by 1.50 centimeter in diameter. If the temperature of the rod increases by 65 degrees Celsius, this change in temperature now, what is the increase in the length? This is very simple. That is delta. You want to find delta L. Delta L is equal to Li alpha delta T. Li is given to be 30. Alpha is given to be this. Delta T is given to be this. Very straightforward. So go and do the other two. Let me have your solution on the LMS page. So you have another exercise here. A poorly designed electronic device has two bolts attached to different parts of the device that almost are the same thing, the same statement as what we have here, the same statement, but I just changed the initial temperature to be 28.70 degrees Celsius. So this is very simple. You just follow the same method. At what temperature will the bolts touch? Take the coefficient of linear expansion for steel and brass to be this and this, the same as I gave have done in the previous example. Then question B says, determine respectively the change in the length of the steel and the brass at that temperature. I believe you know what to do now. You just find the change in length. I even put the formula here. After you have gotten the change in the temperature, you can find the change in the length for the steel. You can find the change in the length for the brass. So this is what I asked you to do. So that is that. Then another one, when the temperature of an aluminum rod was increased by X degrees, that the change in temperature is X degree Celsius. That's your delta T. The ratio of its original length to the final length was this. If the linear expansion of the rod is 11 times 10 to the power minus 6 per degree Celsius, what is X? So please do all this. It's very important you do them so that you can master what we want you to understand as we proceed in this course. So when we resume physically, we might lay our hand on some of them so that you know what to do if you don't understand it. So that is that. So let's move to it and the first law of thermodynamics. It and the first law of thermodynamics. So we soon close this class, but let's look at what we do next. I guess I have 2 more slides and we close the class. Yes. Each and the first law of thermodynamics. So the first thing we are considering under this is heat capacity and specific heat capacity. So the unit of energy is joule and calorie. Joule and calorie. Joule and calorie. 1 calorie is equal to 4.186 joules. So this is the relationship between calorie and joules. And this equality is known as the mechanical equivalent of heat. Mechanical equivalent of heat. So it's known as mechanical equivalent of heat. So let's take the heat capacity first. The heat capacity C, that's capital C, of a particular sample of a substance is defined as the amount of energy needed to raise the temperature of that sample by 1 degree Celsius. So, the heat capacity is the amount of energy we need to raise the temperature of something, the whole something, by 1 degree Celsius. So, I will tell you the difference between the two when we get to specific heat capacity. I know many of you know this right from your secondary school. Well, majority of you don't know. So heat capacity, capital C, of a particular sample of a substance is defined as the amount of energy needed to raise the temperature of that sample by 1 degree Celsius. That is the whole sample. E.g., if the energy needed to raise the temperature of a sample by delta T is Q, then this relationship applies. That is, if the energy needed to raise the temperature by 1 degree is Q, Q is the energy needed to raise the temperature by delta T. So that energy supply divided by delta T, divided by increase in the temperature, will give us the heat capacity of that material. So that when I cross multiply, I have Q is equal to C delta T. This C is capital C, that's heat capacity. If it is specific heat capacity, it will be small c. And small c and capital C has a relationship as this. C, small c, which this is specific heat capacity, now it's equal to capital C over M. So that when you put this, when you put a small c, which will be capital C over M in this equation, you will have Q over M theta. Sorry, C is equal to C capital C over M, and your capital C is Q over delta T. So when I divide the C by M, I need to divide this also by M, and that's what is called a specific heat capacity. So small c is equal to Q over M delta T. When I cross multiply, it will be Q is equal to MC delta T. That's why you have this formula. That's why you have this formula. Many textbooks will use theta as the temperature change, but you can still use delta T. So in this course, I'll be using delta T for temperature change. So C is equal to Q over M delta T. When it comes to light, you have the formula for the heat supply to raise the temperature of a unit mass of that substance by 1 degree Celsius. Okay, let's now define specific heat capacity. Specific heat capacity is the energy needed to raise the temperature of a unit mass. Consider this statement very well. This is the difference between the heat capacity and the specific heat capacity. To raise the temperature of a unit mass of that sample by 1 degree Celsius. Heat capacity will tell you that to raise the temperature of that sample by 1 degree Celsius, but specific heat we say to raise the temperature of a unit mass of that sample by 1 degree Celsius. That's the difference. That's the difference. So specific heat capacity is a measure of how thermally sensitive a substance is to the addition of energy. how thermally insensitive a substance is to the addition of energy. That is how will the substance respond to the change in heat, or to change the temperature. When you supply temperature, how will it respond? That can be determined by the specific heat capacity of that material. The higher the C, that is the higher the specific heat capacity, the more energy must be needed to a given mass of that material to cause a particular temperature change. The higher the C, the more energy it will supply to a unit mass of that body for its temperature to change at all. So I think we can stop here, and if you have any question, we can discuss it before I close the class. So let me try and unmute you people so that you can ask a question. Allow us. So you can unmute yourself and talk, ask question. Let's
Good morning,
discuss.
sir.
Yes, sir. Sir.
Good morning.
Good morning, sir.
Yes.
Good morning, sir.
Yeah, good morning. Good morning.
Sir, the
Yes,
exercise
I
you
can
gave
hear
us. The exercise you gave us, sir.
Okay.
The number 3.
The number 3. Okay.
Yes, the last one, number 3.
Yes, okay, this one.
Yes.
Okay.
The initial length of the 2 bolts are not given.
Oh, I say use all this. Okay. What I will do is that
Okay, sir.
it's still the same question. I just changed some things there.
The values,
Do
okay,
you
sir.
understand?
Yes,
just
sir.
use this picture here. Thank you for that.
Okay, sir. Thank you, sir.
Good morning, sir.
Okay. Good morning, sir. Good morning. How are you?
Good morning, sir.
Okay. Ask your question.
Good morning, sir.
Yes, I can. I'm listening. How are you?
Concerning
I
attendance,
can
are
hear
we
you,
going
but
to
your
take
network
attendance?
is. You said?
Are we going to take attendance?
Yeah, it's already recorded now. Yeah. I'm already taking it.
Good morning, sir.
Good morning, sir.
Good morning, sir.
Good
Good morning,
morning.
sir.
Good morning. How
Good
are
morning,
you?
sir.
Good morning, sir.
Good morning. Yeah.
Sir, please,
Okay.
can you please explain that, or that you explain that part of that alpha change over L over L1 to that alpha change it T? I don't understand that part, sir.
Okay. Which part? You made this. Okay. This
Yes,
part, Abi.
sir. Yes. This part, sir. No.
Okay.
That alpha part, they change in L over L1. Yes, this part.
Changing L. Okay.
Yes, sir. This part.
Okay. You know that this is the formula for what's it called? The initial volume, right? And after you have increased the temperature by delta T, this length, the original volume, will increase by delta N. The width also will increase by delta W, and D, the depth or the height, will increase by delta T. So this is the final depth, this is the final width, and this is the final length. So if I multiply the 3 of them, I get my final volume of that box. You know,
Good morning, sir.
L, yeah, I'm listening. You know delta L is equal to alpha Li delta T. So also will be alpha Wi delta. It's just the letter that is changing. For length is Li, for width is Wi, for depth is Di. So wherever I see delta L, I will put this in there. So I see delta, put this in here. Here I see delta W, I put this thing here. Here also, I see delta D, I will put this thing here. So that my final volume, this volume will become this. So what I did is that I factorize, look at it here and here, Li is common. Here and here, WI is common. Here, DI and DI is common. I factorize LI, WI, DI out. That's why I have this equation I have here. Sorry, that's why I have this equation I have here.
Good morning, sir.
I have how are you? So
I'm
I
fine.
have
Please, sir.
What
LI,
the
WI, DI.
question you gave us?
Okay, hello, somebody. I'm explaining to somebody. Let's go through with our own first, so that we can listen to another question. So the person that asked this question, has your question be answered?
Yes, sir. Thank you, sir.
Oh,
Good
okay.
morning, sir.
Yeah.
Good morning, sir. About the
Good
example.
morning.
Sir, I want to ask a question.
Suraju, how are you?
Good morning, sir.
Please, can you explain that side of
The
young
first four you gave us.
No, I cannot hear you.
Yes,
sir.
Talk one after the other now.
Good morning,
Sir,
sir.
please ask question concerning
Good
our
morning, I'm
going to be
listening.
submitting our assignment, sir.
Can you explain that part that has modulus again?
Modulus. Okay, that's an example. I mean, where is it? Is it up here? Okay.
Yes,
Good
sir.
morning, sir.
Yeah, how are you? Okay, this question, Abi.
Yes, sir.
Okay, they said suppose the ends of the ray are rigidly clamped. That is, you have a ray. Like, let me use a normal English so you understand now. You have a rod that is laid on the road for your train to pass, but you now clamp it. That is, you use both to clamp it down so that when the temperature increases, it will not expand. You don't want it to expand. That's why you clamp the two hands. You clamp this, the first hand. You clamp the second hand. Now they are now asking you to calculate the thermal stress that that rod will be passing through.
I don't know.
The way we tackle this, okay, wait, let me meet these people first so that we can listen to this question. Okay, listen to the solution now. So suppose the end of the ray are rigidly clamped at that temperature, initial temperature, so that it did not allow expansion to occur. That is, maybe you fix the first end, maybe with both, so that when the temperature increases, it will not expand at that end. Then you fix the second hand also, so that when the temperature increases, it will not also expand. They are now asking you to calculate the thermal. You know, that thing we want to expand, but because you have clamped the two ends, it will not be able to expand. So it will be passing through some kind of stress. They say calculate that thermal stress. The way to get it is to calculate it. You know, if you allow expansion, you can calculate the thermal stress. Now say the thermal tensile strain, right? You can calculate the tensile strain. The tensile strain that we get if you allow expansion is the same thing as the thermal stress that thing will pass through if we did not allow expansion. So okay, let's go to the solution now. I said the thermal stress is the same as the tensile stress in the situation in which the ray expands freely, in which you allow expansion to occur. Let's say you allow expansion to occur, you can only calculate the tensile stress that you did in SS1. So, you know, I want to relate tensile stress and tensile strain now. And what relates them is the Young modulus. Young modulus is equal to tensile stress over tensile strain. So this tensile stress is what I will calculate, and that's the thermal stress that thing will be passing through. So you calculate tensile stress if you allow expansion, but that's how to get thermal stress also. So I just cross multiply. If I cross multiply, my tensile stress will be Young modulus times tensile strain. So this was tensile stress, and the formula for tensile stress that we know before is force times area, but there's no force in this question. There's no area, we cannot calculate it. So that's why we use Young modulus times tensile strain. Tensile strain can be calculated using this formula: change in length over original length. So Young modulus given in the question is this, and the change in length we have calculated is 0.013 divided by original length, which is 30.0 meter. So when you divide this by this, multiply by 20 times 10 to the power 10, you have as the thermal stress. It's the tensile stress you calculated, but it's the same thing as thermal stress if the expansion is not allowed. So is that clear? So let me omit yours so that we can talk.
Excuse me,
So you
sir.
can
Yes,
omit
sir.
yourself and talk. Okay.
Hello, sir. I have 2 questions, sir.
Okay.
First one is very simple. Our assignment. Someone said
Okay.
we are not permitted to snap
Yes,
our
sir.
assignment
Sir,
and
can we
submit, sir.
snap our assignment and convert it to PDF and then submit, sir?
No,
Proceeding on number 1.
though, hello, but snapping your assignment will not be allowed.
Bro, keep quiet now.
It will make you unserious. You will not be serious. I want you to type it. You have a system. You have a system. Just type it.
Good morning,
Like that,
sir.
or you convert to PDF and submit.
Good morning.
In this, hello,
Sir,
is
how
that
many
clear?
of
What's your
these
second
are we
question?
to submit, sir? Is it the only one on the LMS or the rest, even including the ones you showed us on the slide now?
I don't want to shut up.
Okay, this question, hello, this question with red something.
Yes, sir.
You might not hello, listen. You might not submit this. Don't submit it, but try and solve this question.
All right.
Do you hear? Don't submit this question. I'm talking now. Don't submit this question to the LMS.
Concerning this question, I have a question also.
Okay. Okay.
Yes, sir. Next time we're going to get
Okay.
diameter. Are you going to convert it to radius or are you just going to solve it in that diameter? So you know the standard for solving if does not support diameter solution. So are you to convert it to radius or still leave it in diameter?
I did not get that question.
So, you know, if you have to start unit for solving.
Okay.
Yes, yeah. So with what I've learned, diameters is not usually supported. So I'm asking that are we to convert it to radius in this question or to leave it in diameter and solve it in diameter?
You know, this is a laser glass rod. They call it rod. You know the meaning of rod. What can I use? It will have it will look like a cylinder, a very long cylinder. So the top, that's the cross-sectional area. That's what you need to calculate before you can get diameter. You need to get. So I'm already solving the question. You need to get the area. When you increase the temperature, the top of it, like the cross-sectional area now, will become wider. That means the area also increases. Definitely the radius or the diameter also will increase. So you just calculate the what's it called? The area. You can calculate the initial area, then you get the initial the final area out from where you can calculate the diameter. But there's no way you can use you cannot use delta diameter is equal to original diameter times alpha. You cannot use that. You have to go from area to get your diameter. Do you understand?
Yes, sir.
Good morning,
It is
sir.
area that.
Good morning, sir.
Proceeding on number 1.
I have a question.
Okay.
Good morning, sir.
Good morning,
Please, sir,
sir.
can you
Good morning.
highlight the
Sir,
assignment?
please, can you explain that number 2 again?
Sir, which
Number
assignment
three.
are we to
Number 2
solve?
again.
Number 2 or 3?
Number 2, please, can you explain it again? This number 2, sir.
Oh, okay, this one.
Yes, sir, the diameter
Do you
that
know
the guy asked.
the diameter part? You know, here I will use delta L is equal to Li alpha delta T. But in case of diameter, you cannot do that.
Okay,
Because
sir.
don't forget that you have a rod. This thing is like a rod, like a cylinder, a very long cylinder, because it is a glass, it's a rod. It's like a very long cylinder. Now we have top. That top is like the cross-sectional area. So you know when you increase the temperature, that cross-sectional area also will get wider. So that means the area also has increased. So you can calculate the increase in that you have delta A is equal to AI, that's initial area. Then what is your, what's it called now? What is your coefficient of area expansion? That's beta. Delta A. That sorry, somebody was calling me. I needed to cut him off. So to get diameter, you need to go from area before you can get your diameter. So I can get change in area. Delta A is equal to AI, that's initial area. Beta, the beta is coefficient of area expansion, delta T. If I can get change in the area, I can get a final area. And since the diameter is given here, you can calculate initial area. Then you can now calculate the diameter from that final area. This initial area will be what? Pi d square over 4 or pi.
I let all the assignment again.
R square.
Excuse me,
Then the
sir.
final, yes.
And now we are having like two assignments to submit. The first one you gave us, that you showed us,
Okay.
and the other one that is on the other slide that has a question like the one you just solved for us. This one.
This one. Okay.
Yes.
Okay.
So we are having this one to submit and the other one, right?
You are submitting this?
Okay. This one. Okay.
Do we have, okay, you are submitting this?
Okay, this one. And yes, and this
one.
Yes.
And this
Good morning.
This
Excuse
one.
me,
Good
sir.
morning.
Good morning.
Yes. Yes,
Please,
I'm
Sir,
listening.
please, sir. Considering on number one, sir.
Okay.
Sir, I listening, sir. Sir, number one, you said gamma. When we want to calculate for gamma, you use the volume. You said volume is equals to the length, the width, and the depth. So, sir, when you now said
I don't know where you are.
Sir, when you want to calculate for the gamma, when you are deriving gamma is equals to 3 alpha.
Okay.
Yes, sir. You said the volume. You said you start from the initial volume. So, sir, when we now want to calculate for beta, when we want to calculate for beta is equals to 2 alpha. Then when we are going to use initial alpha, it would now be length times width only.
Yes, now. Exactly.
Okay.
Good morning.
You know, area is got to length and breadth. Hello, I'm listening. You can just take any of the two. You see, arrive at the same thing, but just use length and breadth.
Thank you, sir.
Okay, I'm listening.
I do not know if it is right for me to ask.
Let that guy ask his question first. Hello, guy, ask your question.
Yes, sir. I don't know if it is right to ask this, but concerning the previous slide, the last assessment, last exercise that you gave us, that you solved, please, I did not understand.
Which one? You mean the lecture 2, right?
Yes, because there is network issue that is, so I did not.
Okay, I'm coming. You see this?
No. Like,
you see this?
No, sir. Concerning the Pascal thing, atmospheric.
That means you joined late. I explained before we started this class. What's the question? What's the question now? This is it now. This is the question. This is the question.
The question.
Is it? Is it the one?
No, sir.
Which one again? I don't think I gave you any other.
Thermodynamics slide, the one about temperature scale.
Oh, temperature scale. And it's saying, okay. Okay. But it's in the first lecture or second lecture?
That would be the second lecture. That's probably what he's asking.
Okay, let me see. It should be here. Okay, this one. You made this one?
your screen. You're not sharing the screen.
You see this? Okay, I'm not sharing my screen. Oh, thank you. What's lecture 2? Okay, you see this?
No, not
this one.
Not this.
No, sir. The first one, the one you explained before we started.
Before we
That's this one.
Yes, sir.
Yes,
That's
sir.
what I was. Oh, because I did not share it. Sorry. So which one are you talking about?
This question, sir.
Okay. I said listen. Okay, let me meet you guys so that we'll be able to. I think after this we need to call it a day. Okay. A constant volume gas thermometer is calibrated in dry ice. You know, I told you if you want to calibrate a thermometer, you need to put it inside the natural system. And I told you the meaning of natural, it can be ice, it can be anything that defines a fixed point. Now they wanted to calibrate this thermometer. They put it inside dry ice, and dry ice is carbon dioxide in the solid state, which has a temperature of -80. So the lower point of that thermometer will be -80. You know, normally the lower point is always 0 for Celsius scale, but now this is the natural material they use to calibrate is -80. And in boiling ethyl alcohol, that's 78.0. So this will be the upper point of that thermometer. So the two pressure are at 0.900 atm and 1.65 atm. And I told you, you can convert this one to Pascal or Newton per meter square, or leave it like that. You still get the same result. So the question is saying, determine the fundamental interval of the scale. Determine the fundamental interval of the scale. You know, how can I get the fundamental interval? The upper point minus the lower point. Upper point is 78. The lower point is this. So it will be 78 minus 80. That's why we have what we have here. Yes, that's why I have 158 as the fundamental interval of that scale. So let's go back to the question B. Question B is saying, what Celsius value of absolute zero does the calibration yield? What Celsius value of the absolute zero does the calibration yield? So what is the meaning of absolute zero? That's the temperature at which the pressure is zero. So I just draw two lines, this one for pressure scale, while this one for temperature scale. So one pressure, the lower pressure given is 0.9, I think. 0.9. I just multiply this by 1.01 times 10 to the power 5. That's what I was saying, approximately 10 to the power 5. 1.01 times 10 to the power 5 to have what I have here. And the temperature there is -80 degrees Celsius. That's the lower point, lower fixed point of this thermometer, -80. And the pressure there is this value. Then the upper is 78. And the pressure there is this value, 1.65 and 10 to the power 5 Pascal. So just consider this one as the fixed point on that thermometer and that pressure scale. The question is now saying, what Celsius value of absolute zero does the calibration yield? So the question is that what is absolute zero? Absolute zero is the temperature at which the pressure is zero. Just go to the pressure scale and put zero there. So the pressure is zero here. That means this temperature here will be absolute zero temperature, because it's at the temperature at which the pressure is zero. So this is what they want us to calculate. So I can now pair them. I can start from anywhere, but whatever you do to the temperature scale must be done on the pressure scale. Okay, from my formula now, I have PL minus PR. Which one's PL? This is PL here. That is lower pressure. Minus the PR, that's the reference. So it will be minus 0 over PU. PU is 1.65 times 10 to the power 5 minus PR. Look at it. Minus PR minus PR. It must be the same like that. And you do the same here. TL is what now? TL is minus 80. The lower fixed point of that thermometer, minus 80. Then minus TR. What is TR? That's TAB, the reference, the one we are interested in. That's why I call it reference temperature or reference pressure. So that's minus 80 minus TAB. Then over the upper PU, that's 165 times 10 to the power 5 minus the reference on that pressure scale, that's 0 over upper for temperature. Don't forget that this is upper for pressure, this upper for temperature scale also, minus the reference TAB. So I just cross multiply. I cross multiply like this. I cross multiply like this, and I have this equation here. So I can expand this multiplied by this minus this multiplied by this equals I do this. After that, I just collect the like time. That is, whatever I say 9900 TAB plus this is equal to this. So when you add the two together, sorry, I cannot see. Let me see. Okay, I've seen it. Oh. So you have minus this value here. This value will give you 74100 TAB is equal to the one you have on the right hand side. Then divide both sides by 74100 to get your TAB. So your TAB, the absolute zero of that scale is minus 273.82 degrees. You will see that this value is still close to normal absolute zero temperature. So that's what I was explaining. Then the second one, or the third one now. What is the pressure at the freezing point of water? That means in this case, they give you temperature. They want you to find pressure. You know the freezing point of water now, that's 0. I'll just go to that scale. I'll go to that scale. I'll just write the temperature they give me. This is the freezing point of water, 0 degrees Celsius. I want to find this pressure. So I can still apply my formula. I can have a P naught minus the lower, this 0 now is not the lower fixed point of that thermometer. This is the, whatever they have given us, what will be using. This is just a temperature given, and they want us to calculate the corresponding pressure. So I can have P naught minus lower pressure over upper pressure minus lower pressure. So I will do the same thing. That's the temperature at P naught, that's 0 minus the lower temperature over upper. This is upper temperature minus lower. That's why I have what I have here. P naught minus the lower pressure over upper pressure minus lower pressure is equal to the temperature they give us, that's the freezing point of water, minus the lower pressure, because this the lower temperature, this lower pressure, I must use a lower temperature over the upper temperature, because this is also upper temperature minus the lower temperature. So I just cross multiply again and do some mathematics manipulation. Like this, you cross multiply, you expand, and you collect the light term. If you do that, you have what you have here. So this is the answer. But if it is because the question is given in ATM, I can just divide this thing by 1.01 times 10 to the power 5 to get what I have here. So you still do the same thing to the last question, the boiling point of water. That means the temperature is given. They say, what's the pressure at the boiling point of water? The temperature is given. What's the boiling point of water? That's 100. So I just go to the scale and put 100 here. You know, 100 is greater than 78. So that means that's why it's here. I put 100. They give me temperature here. They want me to find this pressure. I'll still do the same thing I've done while I was doing for the freezing point of water, and get the answer I have there. So I think you can call it a day. You can unmute yourself and talk.
Sir.
Thank you.
Okay.
Sorry,
Okay.
sir, please,
Thank you.
assignment that we to do. Sir,
I cannot hear you. Hello?
sir, please, what assignment that we to do?
Which assignment are we to submit? Like, are we to
I've
do the
said
one
that
for theory
before
or
now.
one?
I've said that before now. I've said, okay, I'm coming. Let me share the assignment again. And after that, we close the
Thank you, sir.
class. Okay. So look at this assignment. Okay, I'm coming. Let me share.
Sir.
Let me share my screen. Coming.
Sir.
Okay. Can you see my screen?
Yes.
Yes, sir. Yes, sir.
Okay. So we are submitting this assignment. Are we see? We are submitting this assignment. Then this second one, you may not submit. If you like, but I've explained what to do. I think I've solved this one. You just find the change in area from where you calculate your diameter. So, volume, you know how to get the volume of this. This is a rod. This is a cylindrical rod. So you know how to get the volume of a cylinder. So you can calculate the initial volume, you can calculate the final volume. So that's what you will do. So if you like, you can submit this or just leave it. But if you submit, fine. If you don't submit, fine. But I will not grade this one because I've explained what you will do there. But it's very important you know how to solve this question.
Please, sir, excuse
So
me,
you are
sir.
submitting, and you are submitting this assignment also. This will be the second assignment, right? And this will be the third. Okay, let me change it now.
Sir.
Yes.
Can't we snap and convert our answer to PDF instead of typing it?
Type it now. You can type it and upload it as a Word document or as PDF.
No, like can't
Please, are we not allowed to snap and
Can't we
convert?
snap and convert it to PDF, sir?
But that will make it hard.
Sir, we are going to write our name and our matric number on it.
You have not done anything by snapping. So don't you
But
have
some
a
of our
system, a
assignments, we
laptop
just
system?
snapped it and converted to
And the
PDF.
test is how to
No,
get the
I
viewer
don't have
direction.
I don't have a laptop, sir. Are we not?
Sir, we don't have laptop.
Okay. Okay.
We are going to write
All
our
right.
name.
All right. Do that. Just understand
Thank
what
you,
you have
sir.
done.
Thank you, sir. Thank you, sir.
Thank you, sir.
Okay. All right.
Thank you,
Thank you very
sir.
much, sir.
Thank
All
you.
right.
Are we
Let's
not
continue
allowed to
here.
Yes,
snap and
Thank you,
convert
sir.
to PDF?
All right. Bye bye.
Thank you, sir.
Yes.
Thank you,
Okay.
sir.
Bye bye.